Hello everyone again. So for part two in today's in this week class, I will go over fundamentals on the principle of concurrency, mutual exclusion, and synchronization. So as you know, the central theme of operating system design are all concerned with the management of process and thread, like processes and threads. So in multi-programming, the management of multiple processes within a uniprocessor system. On the other hand, for multiprocessing, the management of multiple processes would be within a multiprocessor. And for distributed processing, the management of multiple processes executing on multiple and distributed computer systems. And as a matter of fact, the recent introduction of cluster of computers is a prime example of this type of system. So this is about multiple processes and where can we see multiple processes. So fundamentals to all of these areas and even fundamentals to the operating system design is the concept of concurrency. So concurrency encompasses a host of design issues, including communication among processes, sharing of and even competing for resources. Those resources could be memory, it could be files, it could be I/O access. Also in concurrency, it includes a lot of effort to provide synchronization of the activities of multiple processes and allocation of the processor time to processes. So we shall see that these issues actually arise not just in multiprocessing and distributed processing environments, but even in single processor multiprogramming systems. Concurrently mean multi-threads or multiple processes that are running in parallel at the same time. Concurrency arises in three different contexts. The first one is in multiple applications, in particular in multi-programming, which actually was invented to allow processing time to be dynamically shared among a number of active applications. We also see concurrency in structured applications, which is considered as an extension of the principles of modular design and structured programming. As a matter of fact, some applications can be effectively programmed as a set of concurrent processes. And finally, we could also see it in operating system structure. The same structuring advantages apply to system programs, and we have seen that operating systems are themselves often implemented as a set of processes or even threads. So So, as concurrency is more related or connected to the concept of multiple threads or multiple processes running at the same time concurrently, and there are some key terms that are related to concurrency that we need to address each of those terms individually to understand the meaning of each one, starting by atomic operation. So, when we say this code or this function is called atomic operation, means it's a function or even an action that is implemented as a sequence of one or more instructions. These instructions, they appear to be indivisible, which means no other process can see an intermediate state or interrupt the operation. So once it's started, no one can stop it. So a function or action that once it's started as a sequence of one or more instructions, and then no other process can actually interrupt it, that means it's an atomic operation. The sequence of instructions is guaranteed to execute as a group, uh, not to execute at all, having no visible effect on the system state. So either they execute as a group or not execute at all. That's why we call it atomic operation. And they have no visible effect on the system state. And when we have atomic operation, it actually guarantees isolations from the concurrent processes. That means no other process will interrupt this process. So mainly to guarantee mutual exclusion, which we will talk about it later, it might be preferable to convert most of the operations into atomic operations. So the second concept or terminology, or even we call it key terms related to concurrency, is critical section. What is a critical section? So it's a section of code, like, or a segment of code. It is within a process that actually require access to shared resources. Keep this in mind, that a critical section is all about shared resources. And it's a section of code that within a process that will require access to some shared resources and must not be executed while another process is in its corresponding section of code. This is what is a critical section as. So a deadlock means it's the scenario or the situation in which two or more processes actually are unable to proceed because each one of those processes are waiting for each other to do something. So process A is waiting for process B, and process B is waiting for process A. So this is a deadlock. The third one is the life lock. Life lock is a situation in which two or more processes continuously change their states in response to changes in the other processes without doing any useful work. So it's more about some sort of communication between processes in which we see two or even more. They will try to change their states in response to changes to other processes. That's when we say it's a life lock. The concept of mutual exclusion, which has to be guaranteed in concurrently, especially if we have shared resources, is the requirement that when one process is in the critical section, so if this is process 0 and then we have set of code and then this is the critical section of process 0, means mutual exclusion means it's the requirement that when a process is within the critical section, and in this critical section, it accesses shared resources, it accesses memory, it accesses IO device, whatever, that means no other process may be in a critical section that access any of those shared resources. So if we do have a concurrent process P1, and then B1 will not be able to go into its own critical section because now B0 is in the critical section and it tries to access a shared resource. So B1 cannot access this shared resource. That means B1 cannot be in its critical section because now B0 is in the critical section. If we guarantee this scenario in which when a process is in the critical section to access a shared resource, no other process can be in its critical section to access the same shared resource, this is called mutual exclusion. Race condition, on the other hand, is the situation in which multiple threads or even processes, they read and write a shared data item, and the final result would actually depends on the relative timing of their execution or the order they have accessed this shared item and they write on this item. Starvation is another situation which actually we see this a lot, and we need a lot of compromisation about the synchronization of processes to avoid both deadlock and starvation. Starvation is a situation in which runnable process is overlooked indefinitely, so it is waiting forever by the scheduler. Although it is able to proceed, it's never chosen actually. So that's where we say this process is a starving because it is a runnable process, but it's overlooked for infinity. So for mutual exclusion, as I said, in concurrency, we have to guarantee mutual exclusion to avoid deadlocks and to avoid starvation. So mutual exclusion could be done by different methods. It could be done using software approaches, or it could be done using hardware interrupts, which we'll see in next week, or it could be done even using the operating system itself. So software approaches can be implemented for concurrent processes that are executed on either a single processor or multi-processor machine, and they do have shared main memory. These approaches usually assume elementary mutual exclusion. So the idea of enforcing mutual exclusion is elementary or basic at the memory access level. So that's why they are not quite used a lot in modern operating system. We have to involve either hardware mechanism to enforce mutual exclusion or even allow the operating system itself to enforce mutual exclusion. So as I said, these approaches using the software, these software approaches, they usually assume elementary or basic mutual exclusion, and this is more or less means that there's a simultaneous access, whether it's read or write, to the same location in the main memory. It could be granted or not granted based on how you're going to enforce the mutual exclusion. Um, what actually was initially proposed is that Dijkstra has reported an algorithm. So that's a software approach. So we have to go over a code that will actually enforce this mutual exclusion within the application. So Dijkstra started this by proposing an algorithm for mutual exclusion for just two processes. And it was actually designed by a Deutsche mathematician called Decker. And then following Dijkstra, we developed the solution in stages. And then they came up with multiple stages solution. Like they have came across different attempts to provide solution for mutual exclusion using software approaches. And then using the software approach, it has actually the advantage of illustrating many of the common bugs that are encountered in developing concurrent programs. It's still, it has less capability of working on multiple processor systems, and it suffers from efficient manipulation. But it's an alternative solution to enforce mutual exclusion to avoid major problems in concurrency as the deadlock and starvation, and at the same time to provide efficient synchronization between processes that are running at the same time. Let me share with you the different attempts, like the software coding attempts, before the Dicker algorithm was actually developed. So the first attempt over here, um, as I mentioned earlier, any attempt at mutual exclusion, they must rely on some fundamental exclusion, such that when a process is in the critical section, no other process can be in its critical section until the initial process is completed and it's out of its critical section. So using this constraint of um, of forcing a process to wait until the other process executes its critical section, because this critical section has a shared resource. The first attempt was actually by reserving a global variable that is called, like, just like assume you have a global variable called turn. Let's see how the first attempt is actually implemented. In this, we can see we have two processes. I'm going to call this process 0 and this is process 1, and both of them are wishing to execute to their critical sections. And then each process first will examine the content of the turn variable. If the value of the turn is equal to the process ID, so process 0 has an ID 0 and process 1 has an ID 1. Those first attempts are just for two processes. It would be extended later for multiple processes. So for now, for this, I'm just explaining how the mutual exclusion is enforced or could be enforced across different attempts, just for two processes for now. So let's go back to this synchronization. As I said, we do have two processes. Each of those processes wish to execute until it goes into the critical section and then do something within the critical section to read or write or access a shared resource. And then after this, it will leave the critical section and proceed to the regular routine or the set of instructions. So if the value of the turn within each process equals to the process ID or the process number, then the process may proceed to the critical section. This is the same for process 0 and process 1. Otherwise, if the value is not the same as the process ID, then the process is forced to wait. So for example, for process 0, if it checked on the turn and the turn was 1, it will loop forever for within the while statement until P1 is done from the critical section and sets the turn back to 0. At this point, P0 could start. So our waiting process will repeatedly read the value of the turn until it is allowed to enter to its critical section. This process of checking and waiting, checking and waiting, checking and waiting until you are allowed to go into the critical section is called the busy waiting. Sometimes we call it the spin waiting procedure, which is commonly used to enforce mutual exclusion, a process in which it checks on a condition and then it loops for some time until it is allowed to go into the critical section. This is where we call it the busy waiting scenario or procedure, or the spin waiting procedure. Why we call it this? Because the process that is waiting can do nothing productive until it gets permission to enter its critical section. Instead, it must actually line up and periodically check for the value of the global variable turn. And that means it consumes processor time while waiting for its chance to be executed. That's why we said it's busy waiting. The processor is busy, but at the same time, the process is waiting. So what will happen after the process has gained access to the critical section? So if you assume now that the process has access to the critical section, and after it has completed this section, so now the process is done and it leaves the critical section, it must update the value of the turn variable to that of the other process. So if it's 0, like now we are in process 0, yes, my turn is 0, then go and do the critical section. That means process 1 cannot go into the critical section because the turn is 0 at the moment. And then once process 0 complete its critical section, it has to turn the turn back to 1, so process 1 can start. So that means initially we should have a global variable. In coding wise, we should have end as a global variable, turn equal to 0, defined globally for both process 0 and globally for process 1. So in this first attempt to enforce mutual exclusion using just software approach or software procedure, it shows the program for the two processes. This solution actually guarantees the mutual exclusion property, but it suffers from two drawbacks. First, processes must strictly alternate in their use of their critical sections, and that means the speed of the execution is dictated by the slower of the two processes. So if we assume, for example, that B0, like process 0, it uses the critical section only once per hour. So if this is just once per hour. However, process 1 would like to use the critical section as a rate of 1,000 times per hour. That means process 1 is actually forced to adopt the speed of process 0. This is one of the major drawbacks. It has to wait or has to adopt the speed of the other process. A much more serious problem that actually we can see here in this solution is that if one process fails, the other process is permanently blocked, because if it fails, that means no way it would go and set this turn variable back to 1 because it failed within the critical section or even before the critical section. So this variable was not set back to 1 to allow the other process to proceed. So we can see here that the other process is permanently blocked. And this is actually true whether a process fails in its critical section or even outside the critical section before setting the variable of the global turn variable back to the ID of the other process. So these are the two major problems with the first attempt using the software solution. The second attempt is more or less they try to overcome the drawbacks of the first attempt. So what we have seen in the first attempt is that it has a big flow in storing the name of the process or the ID of the process. So it stored the ID of the process in the turn variable. Which the turn variable with them to allow a process to go into critical section, when in fact we need information about the other process as well. Like you cannot just check on your status if it's 0 or not. You have to check on what's happening on the other side with other processes. So in effect to this, we have to allow each process to have its own key to the critical section, so that if one fails, the other can still access its critical section. And to meet this requirement, the second attempt was actually by proposing a Boolean array or vector. They call it the flag vector. So it was defined. So for those two processes, we have a vector of 2 locations. This is the flag of 0. This is flag 0. And this is flag 1, which is the first location and the second location in the flag array. The first location and the second location of the flag array. And then after we define this vector, Boolean vector, it's either 1 or 0, where flag of 0 refers to P0. So if this flag is 0, that means if this flag is 1, that means it's B1, it's B0 turn. If this flag is 1, like flag of 1 equals 1, that means it's P1 turn. So each process may now examine the other's flag, but may not alter it, like it won't be able to change it. And when a process wishes to enter its critical section, what will happen is it periodically will check the other flag until that flag has the value of false, indicating that the other process is not in its critical section. And then once this, so if we're checking the other process, that means we will keep forever doing nothing until the flag of 1 is set to 0. At this point, it's my turn. So I'm going to set my flag to true. And then this checking process immediately sets its own flag to true and proceeds to the critical section. And when it leaves the critical section, it sets its flag back to 0. This is the same for process 1 and process 0 because they are happening concurrently. So for this attempt, as a matter of fact, we have this global variable or this shared Boolean vector that has 2 locations. Initially, we set them to 0. And then we set them to 1 based on the process that will write on this shared variable. So in the second attempt over here to find a solution for mutual execution, it shows that if one problem that we can see it, or like one scenario we could see it, is if one process fails outside the critical region, including even the flag setting code over here. So what will happen is the other process is not blocked. As a matter of fact, the other process can enter its critical section as often as it likes, and because the flag of the other process is always false. However, if a process fails inside the critical section, so if it fails over here, or even after it sets its flag to true just before entering to the critical section, then the other process is permanently blocked. This solution or this second attempt is actually worse than the first attempt because it doesn't actually guarantee mutual exclusion. So if we look to the following sequence of procedure, like process calls, you can see that actually mutual exclusion is not even guaranteed. So if we look to the starting point where B0 executes the while statement and then finds flag of 1 set to 0 or false, that means P1 will execute, and at the same time, P1 executes the while statement and finds that flag of 0 is set to false. So what will happen is B0 will set flag 0 to true and then enter the critical section, and B1 sets a flag of 1 to true and also into the critical section. Now, because both processes are now in their critical section, this program is completely incorrect. And the problem is that this proposed solution is not independent of relative process execution speeds. So at this point, this second attempt to provide a solution for the mutual execution is actually incorrect. So a third attempt was actually developed to come up with a solution to the mutual execution problem, but at the same time doesn't allow a process to be blocked forever. As we can see in the third attempt over here, because a process can change its state after the other process has checked it, but before the other process can enter its critical section, the second attempt failed. Actually, perhaps we can even fix this with a simple interchange so that we go back to the second attempt and simply take this statement. It was originally here. We just like exchange. We just interchange of the two statements as we see in the third attempt in this graph, in this figure. So let's see if there is which execution enforced or not with this attempt. As before, if one process fails inside the critical section, so which means it failed over here, including the flag setting, code controlling the critical section, also we can see clearly that the other process will also be blocked. And if a process fails outside the critical section, then the other process is not blocked. So now this is not providing a solution for blocking processes. We still have blocked processes. Now let's check if the mutual execution is guaranteed or not using the point of view of process 0 for now. Once process 0 has set flag 0 to true, so that means process 1 cannot enter the critical section until after process 0 has entered and left the critical section and set the flag of 0 back to false. So it could be that B1 is already in the critical section. This is another situation. And when B0 sets its flag to true, in this case, B0 will be blocked by the while statement forever. Until P1 has left its critical section, and the same reasoning would be applied from the point of view of P1. And actually, this procedure guarantees mutual execution, but creates another problem. What will happen if both processes set their flags to true before either has executed the while statement? Then each will think that the other has entered its critical section, and that will actually cause deadlock. So the third attempt is not a good solution. So they moved to a fourth attempt to come up with a software solution to mutual execution to overcome the drawbacks of the first and the second and the third attempts. What we have seen in the third attempt is a process sets its state without knowing the state of the other process. That's why deadlock occurs, because each process can insist on its right to enter its critical section. That means there is no opportunity to back off from this position. We can try to fix this in a way that makes each process more differential. What does mean? What does this mean? That means that each process sets its flag to indicate its desire to enter its critical section, but it is prepared to reset the flag to defer to the other process, as we can see in this figure. This is close to a closed solution, but still has some drawbacks. Mutual exclusion is guaranteed using similar reasoning to that what we have seen in the third attempt. However, let's assume the following sequence of events. If we assume that B0 set flag 0 to true, and then B1 sets flag 1 to true, and then B0 will check on flag 1, followed at the same time P1 check on flag 0, keep in mind that both processes are running at the same time. And then P0 set flag 0 to false, and then B1 will set flag 1 to false, and then P0 sets flag 0 to true, and then B1 sets flag 1 to true. This sequence could be extended indefinitely, and neither processes could actually enter its critical section. Strictly speaking, actually, this is not deadlock because any alternation in the relative speed of the two processes will break this cycle and allow one process to enter the critical section. This condition, as I said before, if I remember, is called life lock. So we don't, for the fourth attempt, we do have enforcement for mutual exclusion. There is no deadlock, but we do have life lock. So the third attempt suffer from the problem of deadlock, and the fourth attempt is life lock. Recall that deadlock occurs when a set of processes wishes to enter their critical section, but no process can actually succeed. But with the life lock in the fourth attempt, there are possible sequence of executions that succeed, but it is possible to describe one or more execution sequence in which no process ever enter its critical section. So although this scenario is not likely to be sustained for a long time, that means it's nevertheless a possible scenario. So actually we have to reject this attempt. So you can see that all of these attempts, they started to provide an initial solution to the mutual exclusion and not blocking processes forever. So they were used as seed for the Dekker's algorithm. So in the Dekker algorithm, it provides a correct solution in which we need to observe the state of both processes, either process 0 or process 1. So we could observe this by providing the array variable flag. So we're going to use the variable flag here as well. But as we can see in the fourth attempt, this is not enough. We must impose an order on the activities of the two processes, and this is merely to avoid the problem of mutual courtesy that we have just observed. That means we incorporate the array flag and also the turn variable, which was used from the first attempt. So we're gonna use this variable, which was used from the first attempt. And let me wipe this. So we're gonna use this from the first attempt. And we're gonna use the flag array from the fourth attempt. So in other words, we will combine a couple of attempts to come up with a more sufficient solution to avoid the deadlocks and at the same time to enforce mutual exclusion. So we use the variable flag, we use the variable turn. In this case, the variable turn will indicate which process has the right to insist to enter the critical section. And then the solution that combines both the flag array and the variable turn is referred to as Dekker's algorithm. As we can see here, when process 0 wants, so if process 0 would like to go into critical section, it first sets its flag to 0. And then it checks the flag of the P1. If that flag is false, that means P0 may immediately enter to the critical section. Otherwise, P0 will consult the variable turn. And then if P0 finds that turn equal to 0, then it knows that it's turn for this process to insist and periodically check B1's flag. B1 will at the same point know that it's turn to defer and set its flag back to 0, allowing P0 now to proceed. And then after B0 has used its critical section, then it sets its flag to false to free the critical section. And also it sets the turn to 1. So in order to transfer the control or the right to P1. So we can see in this figure, the Dekker algorithm using P0 and B1, and the function bar begin over here is mainly used to provide a call or like As a matter of fact, it's like a class of the constructor that is used to call multiple procedures at the same time. So it initiate concurrent execution. This is statement. It initiate concurrent execution of procedures 1 and 2. It could be generally generalized. If we could write it down as bar begin, and then like parallelization begin using process 1 and then P2 and then up to Bn. So we initiating concurrent execution of multiple processes starting from process 1 up to process n at the same time. And then this is Descartes' algorithm. The proof is in the textbook, but you don't need to check on the proof of this algorithm. The idea is Descartes' algorithm, it provides a solution for mutual exclusion. So the Descartes' algorithm, the good about it is it provides solution for the mutual exclusion. And at the same time, it avoids deadlocks. So moving forward, what happened is Descartes' algorithm solves the mutual execution problem, but it more or less is like a complex program that is really difficult to follow, and it's the correctness or the proof a little bit tricky to prove. So although there's a proof in the textbook, but a little bit hard, especially for multiprocessing. So what has been done is they came up with another algorithm. It's called the Peterson algorithm. It's a little bit simplified version of the Descartes algorithm, which provide a simple, elegant solution. As before, the global array flag is also used, which indicates the position of each process with respect to mutual exclusion, and also the variable turn is used to resolve the simultaneous conflict between the processes. The mutual exclusion using the Peterson algorithm is preserved, and it's easily considered in the Peterson algorithm. Let's take a scenario. If we assume that B0, assume now we are B0, and once B0, it sets the flag to 0, to true, then means P1 cannot enter the critical section. If P1 is already in the critical section, then the flag of 1 will always be true. And that means B0 is blocked from entering the critical section. On the other hand, mutual blocking is prevented because it will not happen. If we suppose that P0 is blocked in its while loop, so if I assume it's blocked in the while loop over here, that means flag of 1 is true and turn is 1. And that's at this point, P0 can enter its critical section when either flag of 1 becomes false or even turn becomes 0. So we can look to this algorithm as a simple version of the Descartes algorithm to provide simple solution to the mutual exclusion problem for just two processes. It could be generalized to multiple processes. Initially, when we start, we set the flags of the two processes to 0, and then we call the parallelization begin constructor to call a synchronization or of concurrent execution of two processes B0 and B1. So at first glance, it may seem that interleaving and overlapping would represent fundamentally different modes of execution and present different problems. As a matter of fact, both techniques can be viewed as examples of concurrent processing, and both present the same problems. In the case of uniprocessor, the problem stems from a basic characteristics of multi-programming systems, and the relative speed of execution of processes cannot be predicted. In addition, it depends on the activities of other processes and the way in which the operating system handles interrupts, and also the scheduling policies of the operating system. So what are the main challenges and difficulties in concurrency? We summarize them in 3 main points. The first one is sharing of global resources. For example, if two processes make use of the same global variable and both perform reads and writes on that variable, then the order in which the various reads and writes are executed is critical. An example of this problem will be shown in the following lectures when we talk about memory management. Also, it is very difficult for the operating system to manage the location of resources optimally. For example, if process A may request use of an even being granted control of a particular I/O channel and then be suspended before using that channel, it may be undesirable at this point for the operating system simply to lock the channel and prevent its use by other processes. And indeed, this scenario may lead to a deadlock condition, which makes it very hard for the operating system to manage the allocation of resources in an optimal way. The third challenge is that it becomes very difficult to locate a programming error because results are typically not deterministic and neither reproducible. All of the foregoing difficulties that are present themselves in a multiprocessor system as well, because here we can see that the relative speed of execution of processes is unpredictable. A multiprocessor system may also deal with problems arising from the simultaneous execution of multiple processes. And fundamentally, the problems are also encountered in uniprocessor system. So these are the main difficulties or challenges that we can see it in concurrency. And let me highlight or like go over some other key terms that was aligned with concurrency situations. So far, we talked about mutual exclusion. We talked about a little bit of deadlock, some sort of life locks scenarios. Now let's talk about race condition. We say a race condition is a scenario in which we have multiple processes or threads that try to read and write over items, data items, so that the final result will depend on the order of execution of the instructions in those multiple processes. Now, the loser of the race is the process that updates last and will determine the final value of the variable. This is what we call race condition. What are the main concerns of the operating system? So what are the main design and management issues that are raised by the existence of concurrency? We can list the following concerns. First, the operating system must be able to keep track of the various processes. And actually, this is done with the use of process control blocks, which we have described before. Also, the operating system must be able to allocate and deallocate various resources for each active process. At some times, multiple processes, they might want access to the same resource. And these could be processor time, could be memory, could be files, could be I/O. So the capability of the operating system to allocate and deallocate these resources for the active processes is a challenging task, and it's very concerning. Third, the operating system must protect the data and physical resources for each process against unintended interference by other processes. This would actually involve those techniques that relate to memory management, file management, and input-output management. A general treatment of prediction will be found when we address all of different type of management across different file manager, memory manager, and I/O manager. Finally, the functionality of a process and even the output of this process that it produces must be independent of the speed at which the execution is carried out relative to the speed of other concurrent processes. And this is a very challenging task for the operating system to allow this synchronization. So we can classify the way in which processes in concurrent scenario are interacting based on the basis of the degree to which they are aware of each other existence. In this table, we can see 3 possible degrees of awareness plus the sequence of each one of those. We could have process unaware of the existence of each other, or processes that indirectly aware of each other, they have shared object, or processes directly aware of each other, they do have communication primitives available to each one of them. So for the first level of degree of awareness, if processes are unaware of each other, that means that these processes are independent processes that are not intended to work together. The best example of this situation is multi-programming of multiple independent processes. This can either be either batch job, so we could have an example to this like batch jobs, or even interactive sessions, or a mix of both. Although the processes are not working together, the operating system would need to be concerned about the competition of resources. For example, we might see two independent applications may both want to access the same disk or file or printer, and that means the operating system must regulate these access. So the influence that one process would have on another, result of one process independent of the action of other process, the timing of process may be affected, potential control problems that exist when the two processes are unaware of each other, including mutual exclusion, we might see some deadlocks and even starvation. The second level of awareness, which is process indirectly aware of each other, these are processes that are not necessarily aware of each other by their respective process IDs, but at the same time, they share access to some object. This object could be an example like input-output buffer. Such processes exhibit cooperation by sharing this common object. So it would result of one process may depend on information obtained from other process. Also, timing of the process may be affected. Some potential control problems with this degree of awareness include mutual exclusion and deadlock and starvation, in addition to data coherence, because now we have a shared object. The third level of awareness is processes directly aware of each other. These are processes that are able to communicate with each other by process IDs. And actually, they are designed to work jointly on some activity. These processes, we call them, they are exhibiting cooperation through communication. Also, the result of one process may depend on information from other processes, and the timing of process may be affected. The only two problems that we can see when the two processes are directly aware of each other through communication is deadlock and starvation. So several processes actually may exhibit aspects of both competition and cooperation. It depends on the scenarios, whether this situation is productive or not. Their implications should be determined by the operating system. So I will stop here, and then next class I will discuss each of those degree of awareness and the what situation we that might raise and how we provide solution to those problems. And in addition to this, we would go over fundamentals concepts related to deadlocks and starvations. So thank you for listening, and I'll see you next week.